Our life is filled with inventions, wonderful processes that we overlook because they've become so normal. Some discoveries were initiated thousands of years ago, progressing from one amazing analytical mind to the next. What we see today is but the hundredth or even possibly the thousandth iteration of a single spark, analyzed, figured out, and recorded a very long time ago. When we want to find Arabs, or Muslims more specifically, as the first sparks of invention, it's not that easy finding an abundance over the course of the past several hundred years. They do exist, but few and far between. What's evident is that in order for us to hit a larger and more intensely populated presence of Arab inventors, we must go back to the Golden Age of Islam, a full 1,000 years ago. It's truly sad, but it is what it is. Nonetheless, when doing so, one cannot but be flabbergasted at the vast array of invention and scientific analysis and creativity emanating from that period in Arab and Muslim history. And this is what we want to do: acknowledge and pay homage to some of that genius, whose ideas and discoveries still greatly impact our daily life today, and without whose sparks, our lives would be totally different. They are Abbas ibn Firnas and his dreams of human flight, Ibn al-Haytham in his journey to understand and replicate how we humans see, and Ismail Al Jazari, who endeavored to respond to humanity's urge to replicate itself through machines. To invent is not necessarily to complete, but to begin what had never begun before. An invention is rarely born perfect. It emerges as the first spark that others refine across generations. This is the truth worth remembering. What we use today, such as the plethora of surgical tools shaped by al-Zahrawi, exists through long processes of improvement. Yet every process begins with a single question no one had dared ask. Well, up until the point when one person dared to ask it. Long before flight became the triumph of modern engineering, before the names that we recognize so well of the Wright brothers or even the sketches of Leonardo da Vinci filled the popular imagination, there was Abbas ibn Firnas in 9th century Cordoba. Humanity had always dreamed of flight. Ancient myths like Daedalus imagined wings that could carry man into the heavens. Yet these stories remained symbols of wonder rather than scientific pursuit. Ibn Firnas marked a turning point because he treated flight as a problem to study, test, and solve through observation and reason. He transformed aspiration into a real and structured experiment. His work began with careful attention to nature itself. Ibn Firnas studied the mechanics of bird flight, observing how wings curved, how air flowed beneath feathers, and how balance shifted during ascent and descent. He examined how birds used their tails for stability and landing, insights drawn from methodical observation rather than poetic fascination. Though many of his original writings have been lost to time, references preserved in later scholarly transmission, including accounts linked to Jabr ibn Hayyan, the 9th century polymath, who authored many treatises on chemistry, physics, cosmology, and astronomy, suggest Ibn Firnas had the profound knowledge and expertise to conduct such life-threatening experimentation, and so his understanding reflected a mind trained in mathematics and mechanics, disciplines that shaped his calculations and informed the design of his apparatus. When he constructed his flying device, a hand glider-type machine, it was more than an imaginative costume. Contemporary accounts describe a grand, structured frame covered with silk and feathers, designed to create lift and allow controlled gliding. He then launched himself from an elevated position outside Cordoba. Witnesses recorded that he remained airborne for several moments before his difficult landing. This was a documented scientific test, one that sought measurable results. His crash, which fractured his back, became part of the experiment itself, leading him in hindsight to conclude that he had neglected the appropriate tail mechanisms birds use to stabilize descent. What makes Ibn Firnas extraordinary is not that he mastered flight, but that he was the first to pursue it scientifically. In his leap from Cordoba's heights, humanity crossed an intellectual threshold. Flight ceased to be a myth and became an engineering challenge waiting to finally be solved. Few figures reshaped human understanding as profoundly as Ibn al-Haytham. Living in the 10th and 11th century, his investigations into sight extended far beyond abstract reasoning and into careful anatomical inquiry, including studies of the human eye and its structure. By examining how the eye is formed and how its components interact with light, he strengthened his argument that vision depends on external illumination entering the eye rather than energy emitted from within it. This willingness to combine observation of nature with anatomical evidence marked him as a pioneer of experimental science. At the time, dominant theories claimed that sight originated from rays emitted from within the eye, projecting outward to grasp the world. Ibn al-Haytham, though, challenged this assumption. His work, most famously compiled in the Book of Optics, demonstrated that light travels in straight lines, reflects from surfaces, and enters the eye to produce perception. This shift in explanation redefined vision as a physical interaction between external reality and human biology, rather than a mystical extension of human will. One of his most powerful experimental tools was the camera obscura, a darkened chamber with a small aperture that projects an inverted image of the outside world onto a surface inside. He used this device to observe how light consistently forms images when controlled through a single opening. Rather than treating it as curiosity, he transformed it into a repeatable scientific instrument. Through systematic observation, he showed that visual perception can be modeled, measured, and predicted. This insight laid the foundation for understanding that images could be captured through controlled light projection, an idea that would later evolve into photographic technology. The impact of his work spread far beyond his lifetime. Latin translations of his writings influenced medieval European scholars, including Roger Bacon, who expanded upon his methods of observation and optical experimentation. Ibn al-Haytham's emphasis on testing hypotheses through controlled observation became a cornerstone of scientific inquiry, shaping the development of optics across centuries. His legacy moved gradually through lenses, telescopes, and early imaging systems, all of which trace conceptual lineage to his theories of light. Although he didn't invent the modern camera, Ibn al-Haytham established the intellectual framework that made it possible. The camera obscura he refined was not the endpoint, but the opening of a pathway. Through it, humanity learned not only how to see the world, but how to begin capturing it. Please check out our new course on how to navigate Arab identity in today's world, how to define and pinpoint yourself within the various tensions found in the duality of tradition and modernity, the foundations that make us unique, even our contradictions. Unapologetically Arab is a 13-chapter course intent on helping anyone interested in appreciating what it means to be an Arab. Join now by clicking on the link in the video description at either Thinkific or Patreon, and begin your empowering journey of Arab discovery. Mechanical imagination in the 12th century can only start with one man, and that's Ismail Al Jazari. He wasn't merely a builder of curious devices, but a systematic thinker who documented machines with precision, diagrams, and methodological clarity. His famous treatise, the Book of Knowledge of Ingenious Mechanical Devices, is one of the most detailed engineering manuscripts of the medieval world. Within it, he described pumps, clocks, water systems, and most strikingly, automated figures designed to imitate aspects of human action. His work reveals a mind committed to translating natural and biological processes into mechanical systems governed by gears, weights, and water pressure. Among his most remarkable creations was the automated boat carrying a floating orchestra. This device featured mechanical musicians positioned on a vessel, playing rhythmic sounds driven by concealed water mechanisms and programmable systems of pegs and levers. The arrangement demonstrated a sophisticated understanding of sequencing and controlled repetition. By altering the positions of the pegs, different rhythmic patterns could be produced, thereby allowing the machine to perform in varying ways. This made the instrument one of the earliest known examples of programmable mechanical systems, where human instruction could be encoded into physical form. Al Jazari's deeper significance lies in his intellectual shift. He treated human activity itself as something that could be analyzed, broken down, and reproduced mechanically. Tasks such as pouring water, marking time, or producing music were no longer viewed solely as human actions, but as processes that could be replicated through engineering principles. This was a radical departure from earlier thought, where machines were typically extensions of simple labor rather than imitations of life. His work suggests an early intuition that human motion and function could be decomposed into mechanical equivalents. This conceptual leap places him in a lineage that extends far beyond his own century. Modern robotics, particularly humanoid robotics, is built on the same foundational question Al Jazari explored. Can human actions be modeled and reproduced through machines? Al Jazari's work laid the foundations for thinking about machines as entities capable of imitating life. His mechanical figures didn't simply entertain. They proposed a new relationship between humanity and invention. Through his treatises and engineered devices, he demonstrated that motion, rhythm, and function could be designed, controlled, repeated, and where the boundary between human action and mechanical execution continues to evolve. Across a mere 3 centuries, 3 figures stood before limits their worlds treated as fixed. Abbas ibn Firnas approached flight as a problem to be tested rather than a myth to be admired. Al-Haytham overturned inherited ideas of vision through experiment and observation. Al Jazari redefined machines as systems capable of imitating human action. Each replaced assumption with inquiry, turning boundaries into starting points rather than endings. What began with them didn't remain confined to their time. Their ideas evolved through centuries of refinement into aviation, optics, and robotics, shaping how the modern world sees, moves, and builds. Yet this progression hasn't reached a final form. Instead, technology continues to draw closer to human life itself, becoming more integrated with thought, perception, and even the body. What once stood outside us as tools now increasingly blends with what we are. Yet the lesson for us, Arabs and Muslims, is that history doesn't disappear. It changes shape as it moves forward. In that movement, early origins often fade behind later achievements, until the first imagination is no longer easily seen. And so the Arab and Muslim foundation remains present in every step that follows, carried quietly within the systems and ideas that define the present. And that's something we should find pride in, and hopefully, maybe at some point,